Analyzing industrial automation requires an understanding of the specific hardware used in precise motion. A standard servo mechanism consists of three distinct blocks: the command controller, the servo amplifier, and the servo motor. The system's primary objective is to ensure the motor's actual position precisely follows a predefined command trajectory. Precision is achieved through a continuous feedback loop. A built-in encoder measures the physical state of the motor shaft and sends this data back to the amplifier for processing. As shown in this block diagram, the system calculates the error, or E. This represents the numerical difference between the target command value and the current physical position. The system also tracks the derivative of error, or E dot. This value indicates the rate at which the error is changing, allowing the controller to respond to the speed of the deviation. This closed-loop structure is the basis for automated precision. However, its effectiveness relies on the assumption that operating conditions remain consistent with the system's mathematical model. While control models often assume ideal conditions, industrial environments introduce variables that the model cannot predict. One variable is internal parameter variation. This occurs when physical properties change during operation, such as a load doubling the system's inertia from J to 2J. A more difficult variable to manage is the external disturbance. In a simulation, this is often modeled as an oscillating torque load that actively opposes the motor's rotation. When a sudden disturbance impacts a servo, the physical hardware must compensate immediately. If the controller is unequipped for the load change, the result is a visible loss of positional accuracy. Standard linear controllers, such as a basic PID, respond to these changes through a continuous calculation. However, they often lack the response speed needed for nonlinear shifts, leading to significant tracking errors. Maintaining precision under these conditions requires nonlinear strategies, specifically fuzzy logic and variable structure control. Fuzzy logic control, or FLC, provides an alternative approach that does not require an exact mathematical model of the physical system. The FLC architecture shown here begins by taking crisp sensor data for error and the derivative of error and passing them into a fuzzification interface. Fuzzification converts precise numbers into linguistic variables, categorizing states like high velocity. These enter the decision-making logic, applying if-then rules to determine control action. Finally, the defuzzification interface converts the logical decision back into a crisp voltage signal to drive the motor. While FLC is effective at managing internal parameter variations, simulation data shows it has difficulty rejecting active external disturbances. FLC accommodates ambiguity well, but it lacks the high gain characteristics necessary to counter strong, oscillating forces acting on the servo. Sliding mode control, or SMC, uses a different approach, characterized by high-speed, discontinuous switching to force the system into a desired state. SMC operates within the phase plane, where the x-axis is error and the y-axis is the derivative of error. The diagonal line represents the sliding surface. When activated, the current state moves towards this diagonal line during the reaching phase. The control law uses equivalent and discontinuous components to force the state onto the line. Once it makes contact, it enters the sliding phase, following the sliding surface directly to the origin, becoming mathematically insensitive to external disturbances. Despite its robustness, SMC has a significant mechanical limitation known as chattering. At a high magnification, we can see that the state is not moving smoothly along the line. Instead, it is zigzagging back and forth across the surface at a very high frequency. While this high-speed switching provides disturbance rejection, it introduces mechanical stress and heat that can damage the amplifier and the motor's gear train. Sliding mode fuzzy control, or SMFC, is an architecture that combines these two methods. It seeks the robustness of SMC without the associated mechanical chattering. This utilizes a Takagi-Sugeno fuzzy framework. Unlike standard models, the output of a Takagi-Sugeno rule is a crisp mathematical function rather than a fuzzy value. In this configuration, every fuzzy rule acts as an independent sliding mode controller localized to a specific part of the phase plane. This creates a moving switching surface. The line's slope and intercept adjust dynamically based on system position. To prevent chattering, a boundary layer surrounds the surface. Inside it, control action is interpolated, smoothly curving the trajectory toward the origin without high-frequency switching. By dynamically adjusting the sliding surface geometry, the system maintains low tracking error while eliminating the oscillations that cause mechanical wear. The performance of these controllers was evaluated in the 2011 iJet AET simulation study, which tested their response to extreme operating conditions. In the third test case, the controllers had to maintain position while subjected to an oscillating torque disturbance. Under this load, the standard fuzzy logic controller fails. The actual position diverges significantly, oscillating against the external force. When SMFC is applied, tracking remains stable, following the desired command with almost zero deviation. Data indicates the sliding mode component provides necessary gain to reject the torque load, while the fuzzy logic boundary layer ensures the motor's corrections remain smooth. This combination of rule-based interpolation and variable structure control addresses the chattering problem in robust systems. The result is a controller that achieves high tracking accuracy under disturbance without exceeding the mechanical stress limits of the servo hardware.
Thank you for viewing. So far, if it gives you some information, hit the like button and subscribe for more such technical learning.